Hello, and welcome to another episode of the Book Club. We are doing the RISC-V Reader. Today, we're going to be diving into Chapter 2. We finished up Chapter 1 last time. Alright, let's see what we've got here. Chapter 2 is RV32I, RISC-V Base Integer ISA. We have a quote from Frances Elizabeth Allen from 1981. Apparently she went by the name of Fran. The only way to realistically realize the performance goals and make them accessible to the user was to design the compiler and the computer at the same time. In this way, features would not be put in the hardware which the software could not use. And we have a little aside about her here. 1932 to present day, so she's still alive. She was bestowed the Turing Award, primarily for her work on optimizing compilers. The Turing Award is the greatest prize in computer science. Okay, Introduction 2.1. Figure 2.1 is a one-page graphical representation of the RV32I base instruction set. You can see the full RV32I instruction set by concatenating the underlined letters from left to right for each diagram. The set notation using curly brackets lists the possible variations of the instruction, using either underlined letters or the underscore character, which means no letter for the variation. For example, and they give an example here, I'll write it out for you guys in Milton. Okay, let's find our space here. I'll put it right over here. So what we have, I need to map the tablet, the pen to map to the display properly. So give me a sec here. There we go. Okay, so what we have here is set less than, and they underline SLT, and then they have curly brackets, so it's like this. And okay. So it's like there's two columns here, and like the first one is underscore underscore, and in this one we have immediate, and over here we have unsigned. So the I and the U. Okay, and let me reposition this underscore to match up with the other one. Okay, so what they're saying is this represents the SLT instruction, the SLTI instruction, the SLTU instruction, and SLT SLTIU. So the different combinations you see, the SLT is set less than, and then the I is for immediate, the U is for unsigned, and you can have, you know, any combination of immediate and unsigned is what that's saying. Now, I don't understand why they put like a row above immediate and unsigned that's just blank. I wonder if that's an error in the book, in the formatting of the book, that they have a blank row. Or it's saying the underscore means no letter for this variation. But what would those variations be? I don't understand. I guess, okay, I understand. Never mind. The reason, so what they're saying here is this right here is blank because if it's not the immediate. If it's not immediate, also, did I? Oh, it's just, I left a little mark there. I thought, yeah, this is an E, immediate, but so immediate, if it's not immediate, they're saying there's no letter to represent that, it's just SLT. And if it's not unsigned, so if it's signed, they're saying you don't like put an S to represent that it's signed. If it doesn't have the U, it's a signed operation. So that's the syntax they're using in this book to describe the ISA, basically. So that's good to know. Maybe not the most helpful for you guys if you're following along without a copy of the book, but I'll try to, I'll try to write them out for you guys or describe them to you in enough detail to understand. So it says, the goal of these diagrams, which will be the first figure of the following chapters, is give a quick, insightful overview of the instructions of a chapter. Now we have 2.2 RV32I instruction formats. Figure 2.2 shows the 6 base instruction formats. R-type for register operations, I-type for short immediates and loads, S-type for stores, B-type for conditional branches, U-type for long immediates, and J-type for unconditional jumps. Figure 2.3 lists the opcodes of the RV32I instructions in Figure 2.1 using the formats of Figure 2.2. So I know this is hard to follow along if you're just listening, but bear with me here. Even the instruction formats demonstrate several examples where the simpler RISC-V ISA improves cost performance. First, there are only, so cost performance ratio is what they're saying there. First, there are only 6 formats and all instructions are 32 bits long, which simplifies instruction decoding. ARM32 and particularly x86-32 have numerous formats which make decoding expensive in low-end implementations and a performance challenge for medium and high-end processor designs. Second, RISC-V instructions offer 3 register operands. Rather than having one field shared for source and destination, as with x86-32. When an operation naturally has 3 distinct operands, but the ISA provides only a 2-operand instruction, the compiler or assembly language programmer must use an extra move instruction to preserve the destination operand. Okay. Okay, so let me read that again because that was interesting. So they're saying RISC-V instructions offer 3 register operands. rather than having one field shared for source and destination. When an operation naturally has 3 distinct operands, but the ISA provides only a 2-operand instruction, the compiler or assembly language programmer must use an extra move instruction to preserve the destination operand. So that's really good to know. It would be helpful to see examples where that's the case, I guess. So I guess we'll encounter that at some point. Third, in RISC-V, the specifiers of the registers to be read and written are always in the same location in all instructions, which means the register accesses can begin before decoding the instruction. Many other ISAs reuse a field as a source in some instructions and as a destination in others. Exempla grata, ARM32 and MIPS32, which forces addition of extra hardware to be placed in a potentially time-critical path to select the proper field. Fourth, the immediate fields in these formats are always sign extended, and the sign bit is always in the most significant bit of the instruction. This decision means sign extension of the immediate, which may also be on a critical timing path, can proceed before decoding the instruction. Okay, before I continue here, we're going to go over the diagrams because they fill page 15 and 16. So figure 2.1, diagram of the RV32I instructions. The underlined letters are concatenated from left to right to form RV32I instructions. The curly bracket notation means each vertical item in the set is a different variation of the instruction. The underscore within a set means that one option is simply the instruction name. So for without a letter from the set, for example, the notation near the upper left-hand corner represents the following 6 instructions: and, or, exclusive or, and immediate or immediate, exclusive or immediate. Okay, so let me just summarize what we have here. So we have, first of all, integer computation, and we have add, curly bracket, and then the top one is blank, and below that is immediate, and curly bracket. And add is underlined and I is underlined. So there's the add instruction and the add I instruction. You have subtract, which doesn't have curly bracket, so it's just sub, sub is underlined. You have and, or, exclusive or, and is underlined, or is underlined. The X and the OR in exclusive or are underlined. And then you have a curly bracket where the top row is blank, and then there's immediate where I is underlined. So that's and, or, exclusive or, and immediate, or immediate, exclusive or immediate. We have shift left logical, shift right arithmetic, shift right logical, and those are in curly brackets. They're SLL for shift left logical, SRA for shift right arithmetic, shift right logical is SRL, and then same thing where it can optionally have an I on the end to be immediate for all 3 of those. You have load upper immediate, which is LUI, add upper immediate to PC, which is AUI PC, set less than, and that's the one we wrote out already. You have controlled transfer. So for control transfer, you have branch, and then curly bracket equal or not equal, and the curly bracket. So it's BR, I believe, or is it just B? I think it's supposed to just be B that's underlined, yeah. So B, EQ for equal, the EQ is underlined, and NE is underlined. So BNE for not equal, BEQ for equal. BGE for branch greater than or equal, and there's also BGEU for unsigned. And then there's branch less than, which is BLT, and then it can also be a U on the end to be unsigned. You also have jump and link, which is JAL, and optionally you can put an R on the end for register. Then we have loads and stores. So there's a formatting issue on this one. The curly bracket is like going through the text, so that is a formatting error, but it's load and store are the two in the that are supposed to be in the curly brackets, and then byte, half word, and word in the curly brackets after it. So you have LB for load byte, LH for load half word, LW for load word, and in the same way SB, SH, and SW for store byte, store half word, and store word respectively. Load byte, half word, unsigned. So here unsigned is not in brackets. So this is, they're saying there's also unsigned for load and only for byte and half word. So LBU and LHU. We have miscellaneous instructions. Fence, which is the instruction is actually fence, like all of it is underlined for loads and stores. And then there's fence.I for instructions and data. And then for environment, there's environment break and an environment call, which is eBreak and eCall. And then control status registers. There's read and clear bit, read and set bit, read and write. All of those optionally can be with an immediate, so that would be with an I on the end. And it's CSR for control status register. Read and clear bit is RC, read and set bit is RS, read and write is RW. So like CSR RC, CSR RCI, those would be for the read and clear bit, and read and clear bit with immediate. So you get the idea there. And I guess I'll write these out for you guys. It'll take a little bit, but so I'll try to show it on the webcam, but I don't expect you guys to be able to read it or see it. But like I say, I'll write it out for you guys. So we have integer computation. We have subtract. We have and or exclusive or. And yeah, this should be underlined. This should be underlined. They wrote exclusive or out and underlined the X and the or. Rather than erasing this and writing it all out, I'm just going to assume you guys understand that. Okay, and then we have optionally taking an immediate. Then we have shifts. So let's see here. Okay, shift, left, logical. shift right, arithmetic, shift right, logical, and all of those optionally take an immediate. SRL, SRA, SLL. Okay? And then there's also load upper immediate, which is LUI. And there's add upper immediate to PC. UPC, AUIPC. Okay. And then we have the set less than, which I already wrote out. Now let's make some more space and put in load in stores. Okay, so load in stores I'm going to put right up here. So we have load store, and we have byte, half word, and word. Okay, so this is L, this is S, this is B, H, W. And then below that, we have load, with optionally either bytes or half word, or not really optionally, but the combination of these, with unsigned. So LBU, LHU. Okay. Now let's put in the miscellaneous instructions. So okay, we have fence, loads and stores. And we also have fence.I for instruction. And data. Now this one they only underlined fence, but I believe that's a mistake. I know in the ISA it's fence.I. Unless they changed that. But if they changed it, it would be the same as fence, loads, and stores, so I don't know. Now we also have environment break and call. So EB, RE break, E call, those are completely underlined. And then we have the CSR instructions. So where am I gonna fit those into this? They put them with the miscellaneous instructions, so I'm gonna try to cram them down here. Control and status register, which is CSR. Read and clear. Read. Here, let's zoom in on this. This is getting way too messy. Read and clear bit. Read and set bit. Read and write. So this is RC, RS, and RW. And then additionally, it can have an immediate. Okay, and then we have the control transfer instructions. So branch and jump and link. So it's going to be like branch, jump, and link. Register. So JAL and JALR. Now for branches, equal, and not equal. And then finally, greater than or equal and less than. And we're going to need to cram in again. These can be unsigned. So these are all B, and then this one is G, E, this one is LT. So that's everything that was diagrammed in the book. Hopefully you guys followed my chicken scratches or my descriptions. But we are going to move on to figure 2.2. And this we've already covered. This is the different RISC-V instruction formats, and we've already covered this on Risky Business. So I'm going to refer you to an older diagram here. If I can find it, there it is. So the instruction coding right here, they have that diagrammed in the book. So they start by showing the R type. They show funct7 from bits 25 to 32, RS2 from, it looks like, bits 19 to 24, RS1 from 15 to 19, funct3 from 12 to 14, RD from 6 to 11, and the opcode is 0 to 6 in the bits. And you can see that in my diagram there, where I have like 7 bits, 5 bits, 5 bits, 3 bits, 5 bits, 7 bits. And you can see in the R type I listed it as funct7, RS2, RS1, funct3, RD, and then the opcode for the R type. And it just continues like that for the rest of them. So it's the same kind of thing you would see if you look in the spec, the user level ISA, and it's the same thing as I've drawn out here. Although this has some more, actually. So we did R type, I type, S type, and U type. They've expanded upon that. They have R type, I type, S type, B type, U type, which we had, and then J type. So we didn't diagram out B type or J type. Let's read the subtitle below the description of the diagram. Figure 2.2, RISC-V instruction formats. We label each immediate subfield with the bit position and the immediate value being produced, rather than the bit position in the instruction's immediate field, as is usually done. Chapter 10 explains how the control status registers instructions use the I-type format slightly differently. Figure 2.2 of Waterman and Asanovic 2017 is the basis of this figure. That would be from the user level ISA that they're referring to there. Now, let me expand this diagram here. Because we have 2 types that I did not document. Okay, so B type and J type. Supposed to be B. Let me just rewrite it. And J type. Okay, so B type, you have immediate 12, immediate 10, 5. So, okay, yeah, they're doing that kind of thing again. So this much is the opcode. Okay, and then bits 6 through 11 are split up in half for immediate 1 through 4 and immediate bit 11. So how far is that? So right here. Yeah, so it's 1 bit for immediate position 11. So I don't know the best way to really draw this here. I'm just going to say 11. And then this is for immediate bits 1 through 4. And then funct 3 is going to be right here. RS1 is the same as usual. RS2 is the same as usual. But then these bits get split up in an interesting way. The high bit, so like right here, is going to be bit 12 of the immediate. And then 5 through 10 go right there for the immediate. So that's going to be confusing to people who are watching this who haven't seen the risky business stuff where we go over instruction encoding stuff. So let me try to explain what's going on here. So you see these bits up here, right? I diagrammed out the different bit positions. So when I say this is bit 11, you're looking at this X right here. So this is a single bit in, you know, this is 32 bits that I've drawn out here. And this bit right here, so what you have is an immediate value. So the immediate is only 12 bits long, okay? So the 11th bit from like this end over here are the low bits, and this end over here is the high bits, right? So imagine an integer, a 12-bit integer where the right-hand side is low and the left-hand side is high, right? This is bit 11, so like this bit, you know, if this was a 12-bit integer instead of a 32-bit, start on the high end and go 1 over. That's this bit in the 32-bit instruction encoding for the B type. And then 1 through 4, so that means this is bit 1, this is bit 2, this is bit 3, this is bit 4. Then you jump way over here. This is bit 5, 6, 7, 8, 9, 10. And then the high bit is bit 12. So those bits make up the bits of the immediate. So it's a 12-bit immediate, but it's split up throughout the instruction. It's split across the instruction encoding. They just kind of shoved pieces of the number where they could fit it in the instruction encoding, basically. But that's how that works. So hopefully that made it clearer what's going on there. Let's go on to the J type. So the J type we have the opcode, we have RD right here. We don't have funct3. Instead, we have immediates. So the rest of the J type is immediates. It looks like it's a 20-bit immediate for the J type. So the high bit is bit 20 in the immediate. Now, where is this split? So we need 10 bits for the next part. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got to be somewhere in here. Let me count that again. 1, 2, 3, 4, 5, 6, 7. So like right here. 1 through 10 for the immediate. And then this is 11. So again, we're counting low on this end. So like 1, 2, 3, you know, counting all the way up to 10 over here, but 11 is back here. And then 12 through 19 is right here. So this is 12 through 19. Again, counting, going from the right to the left. And again, this is where these immediates, we're talking about where you have an instruction, and in the code, you put a constant value that you're passing directly into the instruction. That's an immediate, okay? And that number is being encoded in the actual instruction. And the way they encode it is they split the bits of the number up and they pack it into the instruction in the positions that we just documented here. So it depends on the type of the instruction. If it's a J type, it's a 20-bit immediate and it gets packed like this. If it's a B type, it's a 12-bit immediate and it gets packed like this. So hopefully that makes that clear for you guys. Oh wow, okay, figure 2.3. I'm not going to draw this out for you guys. This fills the entire page. This is RV32I opcode map. Has instruction layout, opcodes, format type, and names. Table 19.2 of Waterman and Asanovic 2017 is the basis of this figure. So again, you can find this stuff in the user level ISA documentation. But what they've done is they've drawn this, like these kinds of diagrams that I've drawn out right here, but they did it for every instruction. So it shows the opcode, the actual bits of the opcode. It shows like all the relevant actual bits of the instruction, and lists where the immediates are, and where like the RS1, the RD, the RS2 are. It shows the name of the instruction, the type of the instruction. So it's a nice handy table. If you buy this book, shout outs to buying the book. If you buy the book, you'll get a nice handy table of the opcode space on page 16 for the core ISA the RB32i. But yeah, it shows all of them. It's got LUI, AUIPC, JAL, JALR, so on and so forth. It goes all the way down to CSR, RCI. But yeah, that's a handy table. So, okay, so the opcode is the bits 0 to 6. What's the 3 bits? Funct3. Oh, right. So like, that's interesting to see it like laid out in a table. Again, you can learn this stuff if you watch the Risky Business playlist on YouTube. You know, go to sonera.risky.tv and, you know, search for like instruction encoding, and you can see where I learned this stuff. So let's demo that. I did the How to Watch Risky Business, the annotated episode guide. Check that out, by the way. And Miblo, when you go to annotate this episode, I never sent this one to you, but I put it in the Risky Business playlist. You can annotate this because I consider it part of the Risky Business series. So like if you go to my Risky Business playlist, Risky Business trailer, How to Watch Risky Business, the annotated episode guide. So it's like the first thing you'll see before day 1. And I'd like it annotated because people can practice using the annotated episode guide by following along with me showing them all the features that the annotated episode guide has. And, you know, they can watch it in the annotated episode guide. Like, that would be really slick, I think. So if I go to Sonera, if I spell it, sonera.risky.tv. So I'm going to click on the query box and search instruction encoding. So we determined to study it in the next episode right here, which was day 10. Day 11, studying RISC-V instruction encoding. It starts at 5:53. So you just, you know, you click this and it's going to start you watching exactly where I start. You know, you see right here, I'm writing instruction encoding in Milton, which is what you see right here. This is exactly when I wrote this, right? This is where I learned all this stuff. So, you know, check out How to Watch the Annotated Episode Guide if you don't know how to use this software, or just figure it out yourself. It's intuitive. But yeah, you can use this to quickly learn all the stuff I learned about instruction coding on Risky Business. Really awesome stuff. But basically, what we have here is the opcodes. So like the opcode for branch instructions is 11000011, okay? But that's for branch instructions in general. That's the opcode just for branch instructions. So how do you distinguish between BEQ, branch equal, and branch greater than equal unsigned, right? Just I picked 2 random instructions from the branch instructions, right? How do you determine those, which one you mean, if the opcode is the same for both of them, right? That's what the funct3 is. So if you look in here, right, you see this funct3? That's what those 3 bits are for. So for branch instructions, there's 1, 2, 3, 4, 5, 6. There's 6 different branch instructions. And, you know, if you count off on your fingers, hello, Snail. Thank you for tuning in. So if you count off on your fingers, 1, 2, 3, 4, 5, 6, 7. So you can hold 7 different possible opcodes with are 7 different unique instructions within a single opcode, because you have those 3 extra bits to determine the instruction. So for the branch instructions, we have 6 of them, so that comfortably fits within the opcode space. So branch equal is the funct 3 is 000, whereas branch greater than or equal unsigned is 111. So that gives you an idea of how that is working. So yeah, like I say, I'm not going to write out this entire table, but check out scenera.risky.tv. Check out the where I learned this stuff, or just look it up yourself, or get a copy of this book and you can see the nice table that they put right here. So let's continue on. So we have an elaboration on the B and J type formats. As mentioned below, the immediate field is rotated 1 bit for branch instructions, a variation of the S format that we relabel the B format. Okay, so B format is a variation of the S format. And that's for the branch instructions specifically. The immediate field is rotated 1 bit for the branch instructions. The immediate field of jump instructions rotated 12 bits for jump instructions, a variation of the U format relabeled J. Hence, there are really 4 basic formats, but we can conservatively count RISC-V as having 6 formats. So what I listed originally was the 4 basic formats. Those are the 4 formats that RISC-V has. But technically, there's 6 formats in that the S type and the U type can be specialized to the B type and the J type, which are technically different. So what's happened here is they've shuffled bits around basically for the immediates is the only difference between them. Okay, so let's continue reading here. There's an aside, so let's read that in the margins. It says sign extended immediates even help logical instructions. For example, X and 0x, a bunch of F's and a 0 on the end, uses only the single instruction and I in RISC-V, but it requires 2 instructions in MIPS 32. Add IU to load the constant and then add. Since MIPS 0 extends logical immediates, ARM32 needed to add an additional instruction, BIC, that performs RX and immediate to compensate for 0 extending immediates. So by sign extending immediates, they're saying that really helps simplify the architecture, basically, if you sign extend your immediates instead of 0 extend. So that's an interesting insight into a design choice they made. Let's keep reading the main text here. To help programmers, a bit pattern of all zeros is an illegal RV32I instruction. Thus, erroneous jumps into zeroed memory regions will immediately trap and aid to debugging. Similarly, the bit pattern of all ones is an illegal instruction, which will trap other common errors such as unprogrammed non-volatile memory devices, disconnected memory buses, or broken memory chips. So that's pretty smart of them to make some common, those 2 common bit patterns illegal so that you catch things like that. To leave ample room for ISA extensions, the base RV32I ISA uses less than an eighth of the encoding space in the 32-bit instruction word. The architects also carefully picked the RV32I opcodes that instructions with common data path operations share as many of the same opcode bit values as possible. Ah, that's interesting. Which simplifies the control logic. So the reason they did it this way, the reason they had the opcodes, like I was just describing earlier, how they split it between like opcode and then funct3, where the opcode represents a more general, like I was saying, how all the branch ones are grouped into a single opcode. Well, that's got to be because in hardware, all those instructions are using common data paths, and so they're having it share as many opcode bit values as possible to simplify the control logic. So if I'm understanding correctly, that's what they're saying there. Finally, as we shall see, the branch and jump addresses in the B and J formats must be shifted left 1 bit so as to multiply the addresses by 2, thereby giving branches and jumps a greater range. RISC-V rotates the bits in the immediate operands from a natural placement to reduce the instruction signal fanout and immediate multiplexing costs by almost a factor of 2, which again simplifies data path logic on low-end implementations. So when I was telling you guys how these immediates are like jumbled around, how the values are kind of split up in weird places, you know, that's not an arbitrary choice that they made. It's not like they put it, it's not like they arranged this stuff the way they did just randomly. It's not random, it's very carefully picked so that it's rotated basically within the instruction itself, because that rotation is equivalent to a multiplication that needs to be done to the addresses by a power of 2, which gives the branches and jumps a greater range. So it's kind of a clever hack that they did. The fact that multiplication by a power of 2 is the same as shifting, like you can do that just by shifting the bits, right? Because it's binary and we're multiplying by a power of 2. Same as if you're in base 10, to bring this back to what you're maybe more familiar with. If you have a number like 15 and you say 15 times 10, right? 10 is a power of 10, the base, right? So 15 times 10, you just shift it over one place. So 15 and then a 0 on the end, right? If you want to shift it the other way, 1.5, that's 15 divided by 10, right? You're just shifting the number. This is the same exact trick works in base 2, right? In binary. And so what they're doing is they're actually baking that into the instruction format because they know they need to do that for those particular types of instructions. And it turns out to reduce instruction signal fanout and immediate multiplexing costs by almost a factor of 2, which simplifies data path logic on low-end implementations. I don't know all the details of what that means about instruction signal fanout, what the immediate multiplexing cost would be like, what the data path logic would be like, because we haven't studied hardware yet. So I don't know what all that is like, but it's safe to say that by the way they arranged the immediates, the way they packed them into these instruction formats, is actually really intelligently chosen to make hardware a lot simpler. So this actually has a pretty significant win in terms of hardware complexity, from what I'm understanding here. So that's cool to see. What's different? We'll end each section in this and following chapters with description on how RISC-V differs from other ISAs. The contrast is often what RISC-V is missing. Architects demonstrate good taste by the features they omit, as well as by what they include. There's also an aside in the margins. RISC-V implementations all use the same opcodes for the optional extensions, such as RV32M, RV32F, and so on. Non-standard extensions that are unique to processor are restricted to a reserved opcode space in RISC-V. All right, let's continue on here. The ARM32 12-bit immediate field is not simply a constant, but an input to a function that produces a constant. 8 bits are 0 extended to full width and then rotated right by the value in the 4 remaining bits multiplied by 2. Okay, so ARM actually does some similar kind of stuff, ARM32, with immediates. That's interesting. The hope was encoding more useful constants in 12 bits would reduce the number of executed instructions. ARM32 also dedicates a precious 4 bits in most instruction formats to conditional execution. Despite being infrequently used, conditional execution adds to the complexity of out-of-order processors. Interesting. So that's why RISC-V doesn't dedicate 4 bits to conditional execution. And it sounds like ARM32 did the same kind of shuffling of the bits around with the 12-bit immediate packed into the instruction, but where they differ is that ARM32 0 extends, whereas RISC-V sign extends. And we saw earlier in the book that sign extending is actually a better way to go. Because let me just see here again. There are a number of instructions that would require multiple instructions if they had 0 extended rather than sign extending. That was their reasoning there for why sign extending was better. Interesting. We have an elaboration on out-of-order processors. It says they are high-speed pipeline processors that execute instructions opportunistically instead of in lockstep program order. A critical feature of such processors is register renaming, which maps the register names in the program onto a large number of internal physical registers. The problem with conditional execution is that the registers in these instructions must be allocated to internal physical registers, whether or not the condition holds. Yet internal physical register availability is a critical performance resource for out-of-order processors. All right. We're going to go on to 2.3, and then I'm going to end it there, and we'll continue Chapter 2 tomorrow. So 2.3, RV32I registers. Or are we already on 2.3? No, it looks like this is... Yeah, this is the start of 2.3, but it... okay, well, there's a what's different section in it, so I thought it was a continuation of the previous page, but I guess it's a separate what's different section. Figure 2.4 lists the RV32I registers and their names as determined by the RISC-V application binary interface. We will use the ABI names in our code examples to make them easier to read. To the joy of assembly language programmers and compiler writers, RV32I has 31 registers plus X0, which always has the value 0. ARM32 has merely 16 registers, while x86-32 has only 8. What's different? Dedicating a register to 0 is a surprisingly large factor in simplifying the RISC-V ISA. Figure 3.3 on page 36 in Chapter 3 gives many examples of operations that are native instructions in ARM32 and x86-32, which don't have a 0 register, but can be synthesized from RV32I instructions simply by using the 0 register as an operand. The PC is one of ARM32's 16 registers, which means that any instruction that changes a register may also, as a side effect, be a branch instruction. The PC as a register complicates hardware branch prediction, whose accuracy is vital for good pipeline performance, since every instruction might be a branch instead of 10 to 20% of instructions executed in programs for typical ISAs. It also means one less general purpose register. Okay, so that's interesting. So yeah, the program counter on RISC-V is not a general purpose register. That's good to know. So yeah, we're going to continue this another day. Thank you everyone who tuned in. And you can follow me at risky.tv on YouTube. You can watch the series at risky.tv. And you can follow me at HMN_risky on Twitter to get updates about the series. Thank you also to everyone who supports me on Patreon. We'll have a alternative to Patreon 2 in addition to Patreon. We're not getting rid of Patreon, but we'll have an additional platform soon for people who don't want to use Patreon anymore. The support is greatly appreciated. It makes this series possible. I don't have anyone new to shout out today, so I will see you guys in the next episode, and stay risky, everyone.